It's going to be a vociferous battle between Rahul and Charlotte today on understanding this process from a theoretical and observable perspective. So let's have our start off.
Okay, thanks, Zach. So yeah, I'm going to start off by giving you a sort of observational overview of what we know about reionization, and I think really what we are pretty sure we know, and then I'm going to, in the interest of this being sort of more provocative in this talk series, I will sort of air some of our dirty laundry from the sort of observational and modeling side, interpretation side of this, and then talk about ways that our observations will improve dramatically in the coming decades, certainly, and then really get back to this question of understanding, because I think this is, Rahul and I had several discussions about this. The crux of this is actually, what can we understand about this process of reionization? So just a very quick overview, reionization is the process by which the intergalactic medium transitions from being predominantly neutral, which we know it was after recombination, we would not see the CMB otherwise, to predominantly ionized today. And we think this reionization was driven by the populations of the first luminous objects, probably stars and galaxies, but maybe also AGN, that transitioned the IgM from being predominantly neutral to predominantly ionized. And we think, as I'll explain in this talk, that this was complete by about redshift of 6, so 1 billion years after the Big Bang. And observationally, is in the last decade or so, is really this actual epoch of reionization has become very exciting because we can directly observe this tail end of reionization. So with the Hubble Space Telescope and near-infrared facilities on the ground, we can observe at redshift sort of 6 to just about 10, and actually start to investigate the properties of objects during this sort of end of reionization. And future facilities, notably James Webb, and also 21 centimeter experiments on the ground, will be sort of focusing directly in this reionization era from redshift sort of 10 to 20. And the real, I think, big sort of issue in reionization is that we do not think we have observed the sources that actually reionize the universe. So if you look at the cosmic star formation rate density as a function of redshift, what we've observed are the points on this plot, but the star formation rate density required to reionize the universe around a redshift of 7 would be something more like this pink line. So we have not observed this number density of galaxies. There's this unseen population out there that are probably doing most of reionization. And so, the sort of fundamental question really in reionization is, we cannot see these reionizing objects directly, but we want to know what they are. When and how did these first luminous sources form, and what were their properties? And one of the, what we would like to be able to do with studying reionization is answer, those questions through looking at the process of reionization. What is the timeline and topology of reionization? So if you think of the universe reionizing like a sort of Swiss cheese growing bubbles of ionized gas, how can we, if we understand how that process happens, can we then answer questions about the properties of the first sources? And I think your sort of takeaway from this talk should be that I think we can do this pretty well. In the next decade or so, I think constraining the timeline and topology of reionization will be done to a pretty high degree of precision. But actually, how do we answer these more fundamental questions about the properties of reionizing sources is a lot more difficult. And I think this is where we need to do a lot of deep thinking about what we actually want to learn from our observations. So when I talk about the timeline of reionization, I mostly mean what is the average fraction of hydrogen in the IgM that is ionized or neutral as a function of redshift. So we think that the IgM is mostly neutral at high redshifts. It becomes ionized today. And I'm not going to go into this plot at the moment. I'll come back to these constraints later, but broadly speaking, the reionization timeline depends on the sort of total integrated star formation in the universe at high redshift. So when we have a lot more galaxies forming at early times, reionization will happen earlier. If you have fewer galaxies, reionization will happen later. And this is balanced really by how, if we think that galaxies predominantly do reionization, how easily ionizing photons can actually escape from these galaxies and get into the IgM. So if that process is very difficult, then that'll push reionization to happening at later times. And secondly, when I mean the topology of reionization, what are the sort of typical scales of bubbles in the IgM? So this is work done by Matt McQuinn, I think, when he was a student here with Lars, where all of these maps show you an IgM that is 50% ionized on average. But you can see that the scales of these bubbles are very different in each case. And that depends typically more on the clustering properties of the sources that dominate reionization. So if we have numerous low mass sources that are less biased, you have this more sort of these little bubbles of sort of more uniform distribution of bubble scales. Whereas if reionization is driven by more highly clustered sources, you have these larger bubbles. There's a sort of more bimodal distribution. And so today I'm mostly going to tell you about two ways that we have and we will be able to observe the timeline and topology of reionization and constrain them, primarily by using observations of things at these epochs. So firstly, by talking about the imprint of the neutral IgM on astrophysical backlights, so galaxies and AGN, which would also, you can also do this with GRBs, and then how we can observe the neutral hydrogen directly itself through 21 centimeter emission. And you can do these types of studies as well in a sort of more archaeological perspective, where you look at how reionization impacts galaxy formation, particularly in dwarf galaxies. But I'm not going to really talk about that today. I'm mostly just going to focus on these probes sort of during reionization. But firstly, we have one of the sort of strongest model-independent constraints to reionization coming from the CMB. So as free electrons are created during reionization, these scatter CMB photons, and that will result in a damping of CMB anisotropies on scales that are smaller than the horizon scale at reionization. So you can see here in black is if we have no reionization, and the sort of lightest blue is when you have reionization happening at very high redshifts. It really damps these modes. And at the lowest L modes, you get more polarization induced, which increases at scales above the horizon scale. And this gives you an integral measure of how reionization has impacted the CMB, but it doesn't really give you information about the timing. So this is the constraint on the timeline of reionization that you get just from using this CMB damping. And you can see that it restricts reionization to happen relatively late, so probably before or after redshift of 12, but the sort of space at lower redshifts is not hugely well constrained. So we can start to sort of push on it from the other direction by looking at these sources that we can actually observe at redshift sort of 6 to 8 and ask, what evidence do they have of how ionized or neutral the IgM is here. And so we can do this using these astrophysical sources as backlights. So you're probably familiar with using quasars as backlights to the IgM. These bright objects emitting lots of ionizing radiation that gets absorbed as the light travels through the IgM. And one of the earliest direct observations of neutral gas in the IgM, significant neutral gas in the IgM, came from observations of quasar spectra. where at redshifts greater than 6, we see these extremely blank absorption features, suggesting that these regions are really very highly neutral at redshifts greater than 6. Whereas at lower redshifts, you see lots of features in this, we call the Lyman alpha forest set, which tells us that there's still ionized gas here. So this transition from ionized to neutral around a redshift of 6 is seen clearly in the quasar spectra. And we also see it when we look at statistical populations of galaxies. So if you look at the galaxies that we select at high redshift and try and look for Lyman alpha emission coming from these galaxies, which is also, which is one of these emission lines that will be absorbed by the neutral gas. Beyond a redshift of 6, exactly the same redshifts, we see a dramatic decline in the amount of Lyman alpha coming from these galaxies. So these two observations are really sort of telling us that redshifts beyond 6 seem to be the sort of pushing on when reionization is happening from the other side. But to make constraints on the timeline of reionization from these types of observations requires us to do a sort of piggyback modeling, which in itself brings in a lot of uncertainties. So typically the way that we try to make constraints in reionization from these observations requires us to understand the variation in the lines of sight, because okay, I didn't see Lyman alpha from this galaxy or these quasars. Is that, what is the variation in the lines of sight? We know that reionization happens probably in a very patchy process. So to account for that, we have to use these very, very large-scale simulations of the IGM, which are not really capable of doing galaxy evolution. So we have to couple that to more simplistic models of galaxy evolution. And then basically what is commonly done is you sort of forward model through these IGM simulations, what are the observed properties you would expect, and then try to infer what the properties of the IGM were that produced a model that looked like your observations. So typically, I've done this looking at Lyman alpha emission coming from galaxies, where we forward model the observed equivalent width distribution of Lyman alpha emitters, and then compare that to our observations to try and infer what the IGM that those Lyman alpha photons traveled through was like. And this is done in the same way for quasar spectra, where you can look at the damping wing impact on Lyman alpha. And these two observations are really starting to map out the neutral fraction timeline. So all of the measurements on here at redshifts beyond 7, or 7 and greater, apart from this pentagon, which is from Planck, are from Lyman alpha emitters and Lyman alpha damping wings from quasars. And these tell a mostly consistent picture that the IGM is becoming really rapidly neutral between redshift of 6 and redshift of 8, which in a sort of very simple model is more consistent with this picture where you have the sort of low escape fraction of ionizing photons coming from galaxies. Reionization is happening later. But in the interest of airing our dirty laundry, there are 2 points on here, these 2 diamonds that are actually the exact same quasar, analyzed by 2 different groups, and they get very different answers for what the neutral fraction was. And that's primarily due to the model that they use for the intrinsic spectrum of the quasar. The problem is you're trying to model something and you don't, that's being absorbed. And so you're only really as good as what your model of the intrinsic spectrum is. And this is true both for the quasars and for the galaxies. So this is, a little concerning. How can we make robust constraints if we're not really sure how to model the backlight sources? But rather than me just kind of hand waving these, saying what these points constrain, there was a nice analysis a couple of years ago from Brad Grieg and Andre Messinger, which looked at the current constraints on the timeline of reionization and asked, what does that tell us about the source population that did reionization? So this doesn't include these new measurements at redshifts greater than 7. So it'll be interesting to see how much those impact this. But they basically just looked at 3 parameters which govern the sort of ionizing efficiency of galaxies, the mean free path of photons through the IGM, which is sort of like a typical bubble size, and the minimum virial temperature which can form galaxies. And the main thing I just want you to see is that they still find this, they really find this degeneracy between whether it was sort of these more faint common galaxies with lower ionizing efficiencies or rarer galaxies with higher ionizing efficiencies. Our current data really can't constrain one or the other. But there is a revolution coming. So the 21 centimeter line, 21 centimeter emission from neutral hydrogen will enable us to directly observe the neutral hydrogen gas in the IGM at, during the epoch of reionization. However, this has been a long time coming. So the foregrounds to this line are immense. I think factors of at least 10 to the 5 greater than the signal. Particularly this 21 centimeter line, by the time it gets to us from a redshift of sort of 6 to 10, is redshifted to about 100 to 200 megahertz, which is like right in the range of where humans use radio waves, which is obviously important to us, but we also want to understand about the universe. So this is taking a while, but there are very intrepid radio astronomers who are prepared to go to very remote places to make these measurements. And I think within the next decade, we will have these types of measurements that will much more tightly constrain reionization. So we're probably not going to get nice, pretty pictures of the ionized and neutral regions. We're going to get something more like a power spectrum. So this, which will tell us about these typical scales of ionized bubbles. So this is a model of the power spectrum during reionization. I think black is at the highest redshifts, going to blue at later redshifts as the sort of bubble scales change. And experiments like HERA, which is being built in South Africa, are sort of able to probe in this regime. And their goal and what they hope to be able to do, given their expectations of their data, is to make constraints on the reionization history that are like this red curve. So compared to what we have at the moment, which is this gray region, which maybe is a little bit tighter now with some of these newer measurements, you can see that what you can do with 21 centimeter is just like orders of at least an order of magnitude better. So I think this timeline of reionization is really going to be tied down by 21 centimeter. However, to believe the 21 centimeter signal, because there are these foregrounds, requires us to cross-correlate with emission coming from galaxies. We want to be fairly sure that if we see what we think is a neutral region or an ionized region, that is in some way correlated with, if it's an ionized region, you expect there to be more galaxies there. You'd expect there to be more Lyman alpha emission from these galaxies and quasars in that region. And cross-correlations are going to be very difficult when you consider the scales of these types of observations. So this is a map of the sort of the scale really probed by an instrument like HERA, compared with some infrared facilities. And JWST is, I don't know if you can even, it's like the size of my pointer is what one JWST pointing is going to be. So to make these cross correlations so that we can actually believe 21 centimeter measurements will require really large surveys. But actually, it's exciting that SphereX was selected, because I think one of the things that SphereX can do will give us a way to do a large scale cross correlation. And then, what more can we learn once we have 21 centimeter? I think the power is actually really going to be in combined constraints. So 21 centimeter, although will clear up these sort of bubble scales and this reionization timeline, to understand what that tells us about galaxy evolution requires us to have some sort of some amount of information already from what we know about galaxy evolution. So again, these types of corner plots where you're looking at properties to do with star formation and ionizing photon escape. In green and blue is where you're using information from galaxy luminosity functions. In pink is using the 21 centimeter power spectrum, and in gray is a combined constraint. And you can see mostly every time you have both constraints, the gray posterior is tighter. But particularly using 21 centimeter, I'm just highlighting the plot that kind of tells you what the escape fraction of ionizing photons is as a function of halo mass. It's a sort of scale parameter. You can see that just with the luminosity function, you have this basically uniform posterior. But if you include 21 centimeter observations, you can actually make a constraint there. Okay, so just in the last few minutes, I want to tell you how this is still not really quite such a pretty picture. And I think in the last year or so, there's been a number of observations that have told us that, although we can learn, that although we have this sort of basic understanding of how reionization is happening, we know that our models are not good enough. So firstly, from the galaxy side, there was an observation of a Lyman alpha emitter with a blue peak at redshift greater than 6. And this was very unexpected because during reionization and at high redshift in general, the IgM is so optically thick to Lyman alpha radiation that all the blue flux here should have been absorbed. So the fact that we see this probably requires this galaxy to already live in a very highly ionized bubble, so that the Lyman alpha photons could be transmitted to us before being absorbed. And this, basically was no one had even expected to have observed this. I guess there was, no, that's not true. Some people had talked about observing this, but most reionization modeling had not built this type of thing into their frameworks. Okay, so we think that some of these galaxies may already be living in overdensities that are reionized. Why not go and observe an overdensity of galaxies and look for Lyman alpha emission? So this was done in this field called BDF by Marco Castellano last year. There were a couple of Lyman alpha emitters known in it, and it was a known overdensity of galaxies. So you would expect, okay, this is an overdensity, it should be reionized, we should see lots of Lyman alpha emission in this region. But it was only observed in 3 galaxies, which was far fewer than you would have predicted if this region was already ionized. So trying to understand, okay, it's just one field, but is there a more complex distribution of neutral gas in these overdensities? And then finally, on the galaxy side again, the only Lyman alpha emission that we've observed from galaxies at redshifts greater than 7.5 is coming from very UV bright galaxies. So again, all right, these things probably live in overdensities that are probably reionized. So I tried to test this and put these very bright galaxies in the most overdense regions in the set of reionization simulations that I use, and tried to see if I could explain the prevalence of these objects. And we couldn't explain it unless these galaxies had extreme emission properties, or unless the bubbles, the ionized bubbles in these simulations, are too small than what is actually in the real universe. So I think these sort of overdense regions are really telling us that there's a lot more physics that we're missing in our simulations. And I think actually the problem is the 21 centimeter measurements are not going to get to these sorts of scales of galaxy overdensities. So trying to understand these things is not going to come just from having 21 centimeter. And finally, one thing that has been observed from the quasar side that's puzzling is a very high scatter in the sort of neutral fraction towards the end of reionization. So if you look along individual sight lines, these are all, the dots are all measurements along individual sight lines of the optical depth to that quasar. And you can see there's a very large scatter, particularly around redshift of sort of 6. And this cannot be explained purely by density fluctuations alone. It would require some other type of fluctuation in the sort of UV background or temperature that is not currently being modeled in most sort of simple reionization simulations. Okay, so in summary, I've told you that at least in some way the future is pretty bright for reionization. We're understanding that we can use the evolving transmission of Lyman alpha from galaxies and quasars to time reionization. And we're finding that the IgM seems to be becoming rapidly neutral between redshift 6 and redshift 8. And that 21 centimeter experiments combined with the large-scale galaxy surveys can very precisely measure this timeline and topology of reionization. But the question is, how do we interpret these types of observations? And I think I ended up coming up with a very long list of questions about what we could actually learn. So, all of these sort of corner plots and things I showed you, we can make constraints from these observations, but the constraints that you make are all down to some parameterization. This escape fraction or minimum mass of halo that forms galaxies. We have to decide what we actually want to learn, and then try to create the simulations and make the observations that can constrain those things. We know that there are things that are missing from our models already that can't describe the observations. What are those things? And vice versa, are there observations that we need to make to constrain the models that we're building? And I think one thing that is extremely difficult, as Rahul will talk about, but I think is increasingly important, is being able to self-consistently, sorry, I'm standing in front of my points, model galaxy evolution and reionization. So, I talked about how we have to make do with these sort of hybrid models where we take an IgM simulation, we create galaxy or AGN models and sort of patch them together. But we would, ideally you want to be able to do this self-consistently, and this is very computationally difficult, but I think will actually enable us to make more robust constraints, both from modeling the IgM and also modeling these sort of backlights where there's a lot of uncertainties there too. And finally, how we connect the scales of observations, where we can have these galaxy surveys on very small scales, whereas 21 centimeter is going to be on much larger scales. So try not to be too pessimistic at this point, but maybe Rahul can come along and solve all of our problems. Thanks.
We have time for probably one quick question from Shmuel.
Yeah, so metallicity. Could some of these things, for example, the scatter that you said that is unexplained, or the high UVs that you see, be explained by the evolving metallicity of the galaxies? Because they go together. At the epoch of reionization, you also have the star formation, forming the metallicity and then exposing to IgM. So could the metallicity effect be explained these?
I don't know to what extent it can explain it, but it must play a role. And it's certainly something that hasn't really been modeled fully. I mean, certainly I know from the sort of the galaxy side, we have very simple models of the sort of galaxy evolution. I at least only try to model Lyman alpha equivalent widths as a function of UV magnitude. I don't include metallicity evolution, and that is something that we need to consider and see how much of an impact it makes. Yeah.
Hi. So I'm Rahul. I'm a postdoc here, and I have the same title as Charlotte, but I'll be talking about this from the point of view of a simulator or a modeler, and what kind of assumptions go into the simulations and the models that we do. And you'll hear me talk a lot about degeneracies because there are many of them, and I'll try to talk about all of them a bit in this talk. So I have the same slide as her as well. So what is reionization? She told you. And she also mentioned all the instruments that are coming along. So that tells us why it is important to start modeling now, because if you want to interpret all the data that comes out of these instruments in the next 3 or 4 years, you have to start now. Okay, so why is reionization so difficult to model? So the reason is that you want to reionize the universe, the whole universe basically, using radiation fields that are generated on sub-parsec scales. So you have star formation and like black holes, AGN for example, that produce radiation fields on sub-parsec scales. Now you have to transmit this radiation through the ISM, the CGM, and finally to the IGM, and this is orders of magnitude larger, right? And so you need to know, in order to know the correct transmission through the ISM, you need to know the properties of the ISM, like you mentioned, metallicity, density, temperature, and then you need to know the metallicity, density, temperature of the CGM, and then finally it goes into the IGM. So this is a pretty complex process, and you need to model all of this in order to get the right reionization history. So what are the main questions we can ask about reionization? So we can ask, what are the sources responsible for reionization? When did reionization happen? What is the duration of this process? How uniform or patchy is reionization? And can we constrain cosmology or just astrophysics of structure formation? By that I mean like feedback models, etc., by using reionization. So let's start with a very simple model for reionization. So you assume that for every neutral hydrogen, you need 1 photon of greater than 13.6 electron volts. So basically it gives you the number of photons equals to the number of hydrogen atoms. Okay, that's a very simple model. But we know that recombinations occur. So if you have a high density gas, then with you have the recombination time scale is less than the Hubble time. And so you need, for some hydrogen atoms, you need more than 1 photon kicking off. And then you need more than 1 photon to totally reionize that gas, right? So you can change this equation and say you need this plus whatever photons are lost to recombinations, basically, right? So again, this is a simple equation. This is also a simple equation. The problem is the terms in these equations are not so simple, right? So the number of photons depends upon the source distribution in the universe as a function of space and time. So is it AGN? Is it stars? How many stars are formed in the universe? Where are they formed? How many AGN or quasars are there? So all those things go into this N gamma here. NH is kind of simple. It just basically depends, the total neutral hydrogen just depends upon the cosmology, the background cosmology. If the background cosmology changes, then NH changes as well. And then the most important point here is the T-rec, where you have, because this is a function of both density and temperature, you need to know the exact matter distribution or the gas distribution in the universe. And only then you can kind of figure out this term of this equation, right? So in order to calculate these terms in this very simple equation, you need to go to very complicated functions which depend upon the underlying cosmology and the astrophysical process that affect these processes, right? And so that's why it's not such a simple model for reionization. So let's first look at the matter distribution in the universe. That can be done by just looking at, for example, dark matter simulations. This was done like 10 or 15 years ago. This is just a slide from the Millennium simulation. You know, this is just the dark matter distribution, zooming in on a particular halo. So this has been well tested. We know these dark matter simulations have very high accuracy. They are very high fidelity. They kind of predict the dark matter distribution very, very well. But then if you want to look at the source models, the sources which lie at the intersection of these filaments, then it becomes complicated again. So you have, for example, the total emissivity as a function of time is the function of AGN plus the integral of the star formation rate density of the universe times the stellar emissivity times the escape fraction. And all of these things are extremely complicated functions which you need to model in order to understand reionization. So for example, in very simple models, they use relations like these, which do not really depend upon the fundamental parameters, the basic AGN properties, but just on empirical relations. So it's quite difficult to understand what you exactly get out using these simple models for AGN or star formation, for example. So instead, people have resorted to large-scale simulations to understand what is going on. So the dark matter distribution, as I said, is given with high accuracy with pure dark matter models. So like 10 years ago, there was enough computational resources to simply paint galaxies on top of the dark matter distribution. So the gas distribution follows the dark matter distribution, paint some sources onto these galaxies, and then do radiative transfer in post-processing to look at the ionization structure. Of course, this model has a lot of parameters that need to be set in order to get the right observable characteristics. So you need to know what galaxies live in what halos, what are the star formation rate of those halos, what are the emissivity of these stars, what are the escape fractions of the stars, how clumpy is the gas distribution, etc., etc., etc. So there are a lot of parameters here. You can go one step higher. You can use hydrodynamical simulations and post-process them with radiative transfer. There, the good thing is the gas distribution is given self-consistently, at least on the large scales. And then if you have a realistic feedback model, then you can kind of get the source functions self-consistently as well. So I think it's good for understanding the large-scale properties, more than 100 kiloparsec scales and stuff. But you still have a lot of approximations. You still need to understand the source functions, the escape fractions, self-shielding due to the gas, the source SEDs, etc., etc., etc. And I think the best possible way to do things is to run fully consistent radiation hydrodynamic simulations, which has been possible in the last few years or so, where the simulation not only follows the hydrodynamics and gravity, but it also does radiative transfer on the fly. So you kind of get, I wouldn't say escape fraction, at least the transmission fraction from the smallest resolution element all the way up to the IGN, right? So these are quite expensive, but so Moore's law works in our favor, and right now we are at a time where we can kind of do large-scale radiation hydrodynamic simulations. Okay, so these are the tools that simulators, modelers basically use. So what has been done, so I'll just give you a brief overview of what has been done and what can be done with these simulations. So let's look basically at the UV luminosity functions and the H1 fractions. So I just take the most recent full self-consistent RHD simulations. So these are called the cosmic dawn simulations. They used 100 megaparsec volume of 4096 cube particles. And they use GPU accelerated radiative transfer to decrease the computing time. And so here you can see the reionization history that they get. The real one is the dot dashed line here. And this is their match to the UV luminosity function. So even though they kind of match the UV luminosity function, the dot dashed line, they don't get the correct reionization history. Okay. So this was in 2016. They said we don't match it, so we increase the efficiency of the supernova feedback, and then now we match it. But the UV luminosity function is quite similar, right? So this is the problem with these simulations now, right? You can change the escape fraction or the supernova feedback model, and then you can kind of match it. So there is a degeneracy between these two, and there is no way to break this as far as we know, right? What this basically tells you is that you need extremely accurate feedback model to capture the large-scale properties of the gas. So for example, I show here the temperature distribution in the left, illustrious simulation in the left, and illustrious TNG on the right. And the only change, well, the major change between these simulations is the AGN feedback model, right? So we had a very powerful AGN feedback model on the left and a more subtle feedback model on the right. And you can immediately see that the temperature, well, this is at redshift 1.8. So as it goes on, you will see that the temperature distribution of the gas is much, much different. Even the IgM, not just inside the halos, but also the IgM is so much different between these two halos. And if you do a post-processing radiative transfer along these simulations, you'll get extremely different results because the ionization state and the temperature of the gas is so, so different, right? So that's why it's so important to pin down your feedback models in order to understand reionization in the first place itself. So here you can see the IgM is so much more hotter than here. Here it's only hot in the filaments, right? So that's why feedback is much more important. Okay. Right, so that's the problem with simulations, but we can still also kind of figure out what's going on. We can still place constraints on a lot of things. So for example, here I show the star formation rate density as a function of redshift. And this is the model proposed by Barkana and Avi Loeb here in 2000, where they said, okay, so you have a photoheating feedback due to reionization, and this should reduce the star formation rate in most of the halos. So you have a star formation increase, reionization kicks in, reduces the star formation rate in halos, so the global star formation rate density falls down. And if you can detect this signal, then you can kind of detect reionization, basically, right? But if you actually look into and do realistic simulations with realistic feedback models, you see that this kind of does not work out. So this is the star formation rate density as a function of redshift. It's the same plot as before. And this is the total star formation rate density derived from the simulations, even with reionization modeled in, right? And you do not see this drop in the star formation rate. And why is that? Because, okay, these are all pink lines, but it's the thickness of those lines which matters. So the thickest one is the most massive halos. The medium thickness is the medium halos, so 10 power 9 to 10 power 10. And the thinnest line is the smallest halos, 10 power 8 to 10 power 9. So reionization basically only affects the smallest halos, and it does not affect the medium or the high mass halos. And those are the ones which basically contribute most to the cosmic star formation rate densities. So even though there is a reduction in star formation rate, you won't see this in the global star formation rate density. So this is where the power of the fully self-consistent radiation hydrodynamic simulations come in. So what about the faint end slope of the UV luminosity functions? So why I'm talking about this is that escape fractions are predicted to be quite low from most of the galaxies. And because they are quite low, many reionization models invoke photons from extremely low mass galaxies, all the way up to the atomic cooling limit, so absolute UV magnitude of minus 13. But you know, there are models which state that supernova feedback and low atomic cooling rates and genes filtering due to photoionization can kind of reduce this slope. But again, if you do self-consistent RHD simulations, you see that even if you have reionization, at least up to order of magnitude of minus 15, you do not see any reduction in the UV slope because the UV slope is already shallow due to the supernova feedback alone. So if you have a strong enough and supernova feedback model, then you do not see an effect of shallowing of the slope due to the UV model. But that's not what you see in observations. The latest results given by lensing kind of predict this here. You see this drop in the luminosity function. We don't know what is going on. You probably need more accurate modeling of these extremely low mass halos to actually understand what's happening at these things. So it's left for future work. Okay, then what about the escape fractions? I've talked a lot about the escape fractions. So I think the The only paper where I know where they did self-consistent calculation of the escape fraction is this one here, where they took the first billion years simulation and they post-processes in RT to calculate the escape fraction. So this is the probability density distribution of escape fractions as a function of the halo mass. So pink is the lowest halo mass and orange is the highest one that they have in their simulation, right? So they see that only for halos of less than 10 per halo mass of 10 power 7 or 10 power 8 or so, you have escape fractions of more than 1%, right? So obviously, because only the lowest mass halos have high escape fractions, they predict that the lowest halos produce the most amount of ionizing radiation. But there's a caveat here. This large-scale simulation, and the smallest halos have 100 gas particles or so. So you really don't know if you can trust any of this, because the escape fractions depend upon the smallest scales, less than a parsec scales, and resolving halos by 100 gas particles does not really give you confidence in these results. But there was a very recent paper by Finkelstein who kind of took this escape fractions as a prior and tried to figure out what a reionization history with these escape fractions will look like. And so that's given in the blue line here. And they find this extremely wide duration of reionization. It's not short at all. You have reionization happening as early as like redshift 12, and it goes all the way down to redshift 5 or so. So this seems unrealistic compared to observations to what Charlotte showed, right? So another thing we don't understand is the escape fraction from galaxies. Okay, you can talk about escape fractions. If you that is dependent on the spectral energy distribution of galaxies. So for example, here I show the Sphinx simulations. Okay, I'll skip this slide. But they show here the escape fractions as a function of time for two different models. One model has just the pure Bruzol and Shalot stellar SED, and the blue line is the BPASS model, which contains SEDs from binary stars, right? And their simulation with just the stellar SED does not reionize the universe by redshift 6, but if they include binary stars, then you kind of get a good enough reionization models. And the reason is, if you have a Bruzol and Shalot model, then the ionization intensity drops precipitously after 5 million years or so. Whereas if you have a binary stars, then you have a longer duration during which you have higher UV emission. And so this gives you a better, higher escape fraction. Of course, I must say that they have tuned the star formation model to get this right? If you change the supernova efficiency, for example, you could probably reionize the universe even with the stellar model. So that's another degeneracy that we should look at, right? So these are the problems. And the other thing, the last thing I'll talk about is can we decide what dominates reionization? For example, AGN dominated versus stars. So here is a simple example where if you have an AGN dominated reionization, then your ionization bubbles are larger and less clustered or more clustered. Whereas if you have a stellar dominated, then you have smaller bubbles and they're more clustered. So if you look at the 21 centimeter power spectrum, you could probably see the difference between a galaxy dominated versus an AGN dominated model. And you say, oh, this is great. 21 centimeter can kind of give us an idea about what's going on. But we're working with Sonak here, for example. If you look at the ionization bubbles in CDM versus warm dark matter, you still get the same thing as the differences between AGN dominated and stellar dominated. So that's another degeneracy here, right? So your basic cosmology also will give you the same results for different parameters. So it's a very pessimistic view here, unfortunately. So there are a lot of factors affecting the observables. You have different sources, different feedback models, different cosmology. You have uncertain escape fractions. And understanding the role of each of these individual processes is difficult because they all interact in a nonlinear manner. So you really need really high quality observations to pin down and reduce the parameter phase space for models. But like forthcoming 21 centimeter experiments, DWST, ALMA, and even like CO and C2 emission line intensity mapping will help break a lot of these degeneracies. So I'll just conclude by saying, modeling EIR is still in its infancy. The lack of high quality observations make this, you can do whatever you want, basically. But upcoming instruments will kind of give constraints on this. And I still think self-consistent RSD simulations with realistic and galaxy formation models that kind of give you realistic supernovae and AGN feedback efficiencies is the right way to approach this problem and solve the lot of degeneracies that are present, inherent within this modeling. Thank you.
So on that humbling note, we can open it up to both of them. But do you want to start off with a question?
So you mentioned that there's sensitivity to cosmology in some aspects of this.
Right.
What do you think the prospects are for the use of some set of observations for constraining cosmology going forward? Is there any specific set of observations that actually can constrain the cosmology, or are you always at the mercy and uncertainty regarding the other aspects of the model?
Okay.
So this is an interesting platform in that regard.
Yes, so you also see the same difference here, right? You also, sorry. Again, here is the same thing. So you have small number of sources with larger ionization bubbles. If you do AGN, you get the same thing here, right? If you have an escape fraction, for example, which is inverse of this one here, sorry. So if you have an inverse of this, so for example, only the high mass halos have a higher escape fraction, you will get the same kind of a 21 centimeter signal, right? So you depends upon the escape fraction, if it's an AGN source or the dark matter or the underlying cosmology, all these are degenerate at the moment.
Right, I understand that, but what's the prospects of breaking some of these degeneracies?
So
you often hear in talks when people talk about EOR that, we'll be able to test cosmological models, for example. Should we just take that as completely BS, given the degeneracies you're describing, or is there hopes of overcoming?
No, so I think the best way to, in my view, the best way to approach this is to pin down stuff which we can pin down, like feedback models, AGN models, which can be pinned down even at low redshift, for example, and then can be extrapolated to higher redshift, right? Even observations of JWST or ALMA of the ISM properties of these high redshift galaxies will give you an idea about how these feedback models operate. Once this is done, then the number of parameters in the model will reduce, right? And this is the way to go, basically. So you have to find observables which you need to find cross correlations, basically. And that's why these emission line intensity mappings will also give you a good idea about what's going on. So this will give you kind of a star formation rate traces. So cross correlation between this and 21 centimeter experiments will kind of give you an idea about where the sources are and what the sources are, or how bright the sources are, and then kind of tease out information from these cross correlations, basically.
What do you think the prospects of success are for something like that?
Okay. I don't know.
Well, I mean, so sort of to add to this, like another observation which I sort of talked about as well was, and Rahul mentioned, is looking at a luminosity function. If with JWST we can get luminosity functions down to very, very faint magnitudes of these redshifts, and actually, definitively say we have seen the cutoff in the luminosity function at low mass ends, I think that's one sort of thing that will really feed back into these things and just like cut out. We don't have to worry about that parameter anymore. And I think that is something that with JWST, with maybe with some help from lensing, like I think the prospects for that are not too distant.
A few slides back here, these two plots on no binary stars and binary stars. Yeah, probably this one or the next one, whatever. So this one, yes, okay. So just to give this, try to push this information to everybody in the audience. You should never ever use Brussels-Charlotte 03 to do this type of work. While you were talking, I just went to Vizier to check. The entire thing on the left is based on 10 stellar spectra, 10, in the stellar library that went in, because Bruzal and Charlot 03 used the stellar library with 10 stars hotter than 20,000 Kelvin, which are responsible for this UV background. None of them has subsolar metallicity.
Right.
Okay, so it's all wrong. You should either use, well, people who did this work, they either should have used the Starburst 99, which is fully synthetic, or didn't talk about it at all. Bruzal and Charlot is not intended to be used to analyze young stellar populations or compute escape fractions. So one should not take this seriously at all.
Okay.
But just to, I mean, what you said is correct, but on the other hand, the general effect is still generically true.
Right.
Take Starburst 99 or any other more modern single star model, you get this very precipitous drop in the ionizing production rate, which has more to do just with the evolution of the turnoff of the main sequence than the shape of the stellar spectrum. And BPAS, the binary models, produces this long tail of ionizing spectra because they're able to produce high mass stars at later times because of binary mass transfer.
Sure.
It's a generic.
Did you hear, do you remember the talk from yesterday on high redshift stuff? They were talking, one of the conclusions, the first talk yesterday, was that metallicity in young population is the predominant factor that regulates extreme UV photons. Here, the metallicity is wrong, so the prediction is totally wrong. Basically, you can make a mistake by 1 order of magnitude easily, just going from the metallicity that Bruzal and Charlot has, which is solar essentially, to metal poor stars, where massive stars are formed more efficiently and stuff like this. So basically, one has to be extremely cautious by using models, correct models, to do the interpretation like this. Bruzal and Charlot are good for all stellar population. They're good to give some predictions on optical colors of red and dead galaxies, things like this. Don't try even to go to redshift 7 with them.
Yes. Well, I think the main point here is that this tail at the end
I
is
understand.
important because
Sure.
you will have, so here most of the ionizing flux happens before the first supernova goes off. So most of it will get absorbed in the GMC itself. Whereas here you'll have a flux after the supernova goes off, so it'll kind of clear out the regions and you can get these funnels through which radiation can escape. And that's the main reason why you get this.
Yeah.
But yes, so I think they have tried Starburst 99. I'm not sure at low metallicity how different it will be, but yes, I take your point.
Yeah, sure.
Can you go back to this plot where you showed different kind of bubbles, ionization? Yeah, these ones. So I wonder, even with the current observations, so if I don't want to wait for the 21 centimeters and just with the Lyman alpha, so when you go to look at the reionization at different lines of sight, and you see at different epochs, so you have a dispersion on this reionization redshift. From the width of the dispersion, you can tell you can constrain the sizes of these bubbles, because if you have very coherent large bubbles, you'll expect large dispersion between different lines of sight. Whereas in this scenario, where you have very small bubbles, so everything is kind of cancels out, and different lines of sight would be more similar. So I wonder if this has been done, and if not, it should be done.
Yeah, so I mean, we definitely should do this. I think we still haven't really got a large enough sample to do this. It's sort of being looked at looking at clustering of Lyman alpha emitters, which can survey a large area, but the volume is actually too big, so the redshift resolution isn't good enough because it kind of washes out this effect. So you want like a very large spectroscopic survey of galaxies, and it is possible, but I think it will take a while to build up that sample. But yeah, we hope we'll be able to make a measurement of this before the 21 centimeter observation.
And the main difference is, I think, you have individual sight lines versus a global
kind
Yeah,
of a
it'll
feel.
never be as accurate as a 21 centimeter.
No,
But you could
no
get
doubt
some
that 21
idea.
centimeter is good.
Yeah,
not,
but it would be nice to
no
have
doubt
some
about
idea.
that.
Yeah.
I'm just saying, what can we do now,
Yeah.
except of
Yeah.
waiting for the 21 centimeter?
I think just to add to that, I think that this kind of connects to what Gibran was bringing up earlier as well as to how we break these degeneracies. Actually, one of the interesting things is not just looking at this at one particular snapshot in time, but seeing how this evolves over time. Because, for example, if you look at that picture of the warm dark matter case, by redshift 6 or something, it actually looks identical to cold dark matter, whereas at redshift 8 it is manifestly very different. And you can actually predict how fast these things should change just purely based on the dark matter physics alone. And that may have a slightly different evolution to what, say, for example, the AGM dominated case. Okay, I think we've run out of time, but thank you all for attending.